Welcome to the lecture on problem solving on phase diagrams. So, in this lecture we are going to have the problem solving session mainly based on the problems related to phase diagrams, and also we will discuss about some problems, one or more problem related to the Schaeffler or Delong diagram. So, which we could not do during the lecture classes. So, coming to the questions. First question is that in the PBSN system, determine the fraction of phase in an alloy of 80% tin at 184 degrees C and 182 degrees C. So, that is the question, and you have to solve this question. So, the temperature, as you see, this is the PBSN diagram, and as you know that your eutectic this is temperature, that is 183 degrees centigrade. So, you have to find for this 80% tin composition, you have to find just above this eutectic temperature and just below this temperature. So, what will be the fraction of phase in the alloy. So, as you can see that 80% is coming into this zone, and once you go to this zone, then in this zone is beta plus liquid, and if you are coming to temperature just below 183, that is 182 degrees centigrade, then you have the alpha on this side and you have beta on this side. So, basically in one case you are getting beta plus liquid, and in another case you are getting beta plus alpha. So, you have to find the fraction of phase beta in the alloy. So, basically that phase will be beta only. So, we are going to have the calculation for the fraction of phase beta. Now, coming to the temperature at 184 degrees C. So, this will be the point, and for getting beta, as you know that you will have a line just above 183. So, for beta, so this side it is beta. So, amount of beta will be this distance divided by the whole distance. So, this is 80%. So, this distance will be 80 minus 61.9, and the whole distance will be, this is 97.8. So, 97.8 minus 61.9. So, if you see the answer of question 1. So, the at 184 degrees centigrade, the beta phase will be, so as you see that we discussed that it will be 80 minus 61.9, which is the eutectic point, divided by it's touching on the another side, on the right hand side at 97.8. So, you will have 97.8 minus and again 61.9. So, we are using this lever rule, and it will be 18.1 divided by, so it is 35.9. So, it will be coming close to 51%. So, that is what you are seeing in this case it will be coming as 51%. Now, if you go to the temperature just below this temperature, just below 183 degrees centigrade. Now, here you will have to if you draw the tie line rule. So, it will be touching one is beta point, another is this is the alpha, for this alpha. So, the beta phase which will be formed beta. So, its amount will be according to lever rule this ratio divided by the whole ratio. So, this ratio will be this is 80 and this is 18.3. So, the beta phase will be 80 minus 18.3 divided by the total distance, that is 97.8 minus 18.3. So, at 182 degrees centigrade, the beta phase will be, so as you know beta is on this side. So, as per lever rule you will go towards left. So, it will be 80 minus 18.3 divided by, on this side you have 97.8 and minus 18.3. So, it will be approximately 78%. So that is what you see in this case. So, this will be this distance divided by whole distance. So, it will be coming close to 78%. So, it will be 61.7 divided by 79.5. So, it will be approximately 78%. So, that is how you can calculate the amount of phase, and if you go to 182 degree centigrade, rest percentage will be the alpha phase. So, you will have alpha as 22% around. So, that is how you calculate the value of the beta phase. Coming to the next question. Now, the next question is from the iron carbide phase diagram for a 0.2% carbon steel, name the phases and their fractions at equilibrium at the following temperatures. So, now we have to find the different phases and also their fractions at equilibrium. So, we have the different temperatures given just above 1493. So, we have to see the iron carbon diagram. Now, this temperature is the 1493 degree centigrade, and we are talking about the composition, that is 0.2% carbon steel. So, this is 0.18. So, you will have 0.2 here, and for 0.2 and just above this it is going into this zone. This zone is this is delta plus liquid. So, this side it is liquid. So, you will have delta as well as liquid. Now, on this point if you draw the line, on one side it will be touching this point and on another side it will be touching this point. So, for finding the end, this is the delta phase. So, amount of delta phase will be proportional to, so that will be its fraction will be this distance divided by the whole distance. So, you have 0.2% of steel, and on this side it is given as it is 0.5%. So, the percentage of delta phase will be 0.5 minus 0.2 divided by 0.5 minus, it is touching here. So, that is 0.5 minus 0.1. So, if you go to answer for question 2, then for first above 1493 degree centigrade, you have two phases. One is delta iron, delta phase, so delta iron, and another is liquid iron. Now, for delta, as you see that delta is towards left. So, using the lever rule, you have to see towards the right where it is touching that liquidus line. So, it is just above that temperature line, it is at 0.5. So, the fraction of delta phase, it will be so you will have 0.5 towards the rightmost point, and we are talking about 0.2%, and ultimately it is going towards 0.1% towards the extreme left. So, it will be 0.5 minus 0.1. So, it will be 0.3 divided by 0.4. So, it is 75%. So, you have 75% of the delta ferrite phase is formed just above 1493 degree centigrade of temperature. So, above the 1493, if you use the next phase is that one is liquid. So, F liquid will be 1 minus 0.75. So, it will be 0.25. So, 25% will be the liquid phase. Now, we have to see the next is that just below 1493 degree centigrade. So, if you come to just below 1493 degree centigrade, okay. So let us see how the we know about what is the phase. So, just below, so we are talking about a point which, so this is 0.18, so this will be 0.2, and just below that it is going into this liquid plus gamma zone. Now, in this liquid plus gamma zone, if you draw a tri-line, it will be touching somewhere close to this on this side, and another point will be just here, that is 0.18%. So, you will have one side is for the gamma, another side is for this liquidous line. So, you have the formation of gamma phase as well as the liquid. So, you have to find gamma. Now, for gamma, since gamma is on this boundary, so the gamma percentage will be for the distance from 0.2% to 0.5%, and that will be respective to 0.5 minus 0.18. So, if you try to find the fraction of gamma, it will be 0.5 minus 0.2 and divided by the 0.5 minus 0.1 is a very technical point it is. So, it will be 0.3 upon it will be 0.32. So, it is coming close to 94%. Okay. So, that is how you are getting the fraction of gamma. So, if you take the next phase, that is liquid only. So, the liquid fraction will be the rest one, that is 1 minus 0.94. So, it will be 6%. So, just below the 1493 degree centigrade, you have the 94% of gamma and 6% of liquid. So, next is so in this question only, then you have to find just above 725 and just below 725. So, if you go to above 725 and that too for 0.2% carbon. So, if you go above 725, now in this case you are getting alpha plus gamma, and if you go just below 725, then in the below 725 you are getting alpha this side, and this side you have Fe3C line. So, above 725 you are getting alpha plus gamma, below 725 you are getting alpha plus Fe3C. Now, percentage of ferrite for above 725. So, if suppose you have the 0.2% line somewhere, so just above that. So, for alpha you have to have this line and divided by the whole length. So, from here to this point. So, you are getting something like 0.8 minus 0.2, and this point is normally 0.02%. So, 0.8 minus 0.2 divided by 0.8 minus 0.02. So, if you go for third part, if you go above 725 degrees C, you have phases are alpha and gamma. Now, alpha fraction of alpha will be using the lever rule, it will be the fraction of the right hand part. So, it will be 0.8 minus 0.2, and then you will have 0.8 minus 0.02. So, it is coming close to 70. So, it will be close to 77%. So, rest will be your gamma, and F gamma will be 1 minus 0.77, that will be 0.23. So, it will be 23%. That even can be calculated, because if you want to calculate the gamma, and gamma is on the right hand side. So, gamma will be 0.2 minus 0.02 divided by 0.8 minus 0.02 like that. So, that way you will get this value only 23%. Now, if you come to the temperature below 725, so below 725 degrees C, as we discussed, we have two phases, one is alpha, another is Fe3C. So, for alpha you have to take the distance from that point to 6.67. So, F alpha will be 6.67 minus 0.2, because the alpha will be corresponding to this line divided by the whole line. So, 6.67 minus 0.2, and then you will be dividing it with 6.67 minus 0.02. So, if you take this value, it will be close to 97%. So, rest will be Fe3C, and Fe3C, as you see, it is, if it is 97%, then it will be 0.03, that is 3%. So, this way you can calculate the values of these different phases. Now, next question will be, you will have the next question, and that question is that what is the fraction of pro-eutectoid cementite in 1.4% carbon. Now, we are talking about the formation of pro-eutectoid cementite in 1.4% carbon. So, this is your about 1.4% carbon. So, this will be somewhere here. So, this is 0.1, maybe somewhere here. Now, what will be, so pro-eutectoid cementite, the cementite which is formed before this eutectoid reaction, what will be that? So, cementite will be corresponding to this length divided by this whole length, because cementite is touching on this side, this is the cementite line. So, it will be corresponding to this line divided by the whole line. So, it will be 1.4 minus 0.8 divided by 6.67 minus 0.8. So, if you go to question answer 3 now, and pro-eutectoid cementite. So, if you take the first part, pro-eutectoid cementite, pro-eutectoid cementite, it will be for 1.4%. So, as we discussed, it will be 1.4 minus 0.8 divided by 6.67 minus 0.8. So, it will be something very much near to 0.10. So, about 10% of pro-eutectoid cementite you will be getting in this case when you have 1.4% of carbon. Now, next is you have 1% carbon. So, for 1% carbon, you are coming again here on this line. So, for 1% carbon again, it will be 1 minus 0.8 divided by 6.67 minus so 0.8. So, it will be, again we have to calculate. So, for 1% carbon, so this is for 1.4% carbon, and this is for 1% carbon. For 1% carbon, F pro-eutectoid cementite will be 1 minus 0.8 divided by 6.67 minus 0.8. So, it will be coming close to 3.4%. So, if you do the calculation, you will get it close to this value of 3.4%. Now, the next question is, next part of this question is 0.7% carbon steel. So, if you are coming to 0.7% carbon steel, it is below this. So, it is below this line, and in that case you know that cementite, it is touching simply here this line. So, in that case it will be 0. So, basically what you see that so that is why this is not coming into picture. So, basically your value in that case will be negligible, it will be 0. So this is how using the different type of phase diagrams you can calculate the fractional amount of the different phases using the phase diagrams. Now, we will have the discussion about the use of the Delong diagram. So, in our earlier lecture we discussed about the Schaeffler diagram, where from that diagram we try to find the weld metal deposit concentration, composition, and apart from that we also discussed about the Delong diagram, where basically the especially for the presence of nitrogen, when you have to analyze, then the Delong diagram is used. So, let us say there is a problem, and the problem is that you have the stainless steel is wire, stainless steel that is to be welded, and it is to be welded using a wire also, that is also of stainless steel grade. So, you have two different grades of stainless steel. One is for the base material, and another is for the wire. So, for base metal and for the filler wire, the different composition is provided, and different composition is in the term of percentage carbon, percentage manganese, percentage silicon, and percentage chromium, percentage nickel, and percentage nitrogen is given. So, as you know that in the case of when the nitrogen is present, we use the Delong diagram, and for base metal and also for the filler wire, the composition is like for base metal it is 0.15 and for filler wire it is 0.05. For the base metal manganese is 10 and this is 2. Similarly, you have 1% silicon in both the cases, and chromium is 17% for base metal and 21% for the filler wire, and nickel is 4% for base metal and 12% for the filler wire, and this is 0.25% in the base metal. So, what you have to do is you have to find the maximum and minimum amount of the ferrite phase which is possible in the weld metal. So, that you have to calculate. Now, for that you need to look into the Delong diagram, and this is the Delong diagram which is given. This Delong diagram, again here you say we see that this is the chromium equivalent, which is calculated using this formula chromium plus molybdenum, percentage molybdenum, and then you have these values are given, plus 1.5 times percentage silicon plus 0.5 percentage columbium, and similarly you have nickel equivalent value also given, and that can be from here you will get the nickel equivalent, and from there you will get these 2 points. So, first of all we will be finding the chrome equivalent and the nickel equivalent values. So, if you try to find the for base metal and for the filler wire also. So, for base metal if you find the chrome equivalent, so chrome equivalent will be as you know that it is percentage chromium plus percentage molybdenum plus 1.5 percentage silicon plus 0.5 percentage columbium. So, that way, so percentage chromium is as you see it is 17, percentage molybdenum is anyway not there. So, then you have 1.5 percentage silicon, so it will be 1.5, and columbium again is not there. So, you will have 17 plus 1.5, that is 18.5. Similarly, if you find the nickel equivalent for the base metal, so nickel equivalent for the base metal will be again for the formula percentage nickel plus 30 percentage carbon plus 30 percentage nitrogen and 0.5% is manganese. So, that is the formula for the nickel equivalent. So, nickel as you see, nickel is 12% for this case. No, nickel is 4% for the base metal. So, 4, and carbon is 0.15. So, 30 times 0.15, it will be 4.5. So, it will be 4.5 plus 30 times percent is nitrogen, nitrogen is 0.25. So, it will be 7.5, and then you have 0.5% manganese, manganese is 10%. So, it will be 5. So, it will be coming to 21. So, for the base metal you are getting the point on the Delong diagram, that is your 18.5 and it is 21. Now, similar way we are going to calculate for the filler wire, and for the filler wire we are going to have the calculation for chrome equivalent, and for chrome equivalent we are going to get again percentage chromium. So, chromium is 21, then you have percentage molybdenum. So, molybdenum anyway not there, then 1.5% silicon, silicon is both in both the cases it is same, and plus 0.5% columbium. So, it is anyway not there. So, it is 22.5, and if you calculate the nickel equivalent, so nickel equivalent will be percentage nickel in this case it is 12, and then you have 30% carbon, carbon in this case is 0.05. So, 30 multiplied by 0.05, that will be 1.5. Then you have 30% nitrogen, 13% of nitrogen. So, nitrogen is anyway not there. So, it will be 0, and further you have 0.5% manganese, manganese is 2%. So, 0.5 into 2 1. So, it will be 14.5. So, for filler wire the point which you are getting, it is 21 14.5. So, it is 22.5 and 14.5. So, your point is 22.5 and 14.5. Now, you have to basically put these 2 points on the Delong diagram. So, you have 2 points, that is 18.5 and 21, and next is you have 22.5 and then you have 14.5. So, 18.5 21 if you go, so 18.5 and 21 it goes to this point, and the next point is 22.5. So, that will be here, and then further you go to 14.5. So, it is coming to this point. Now, what you see, these are your ferrite numbers which talks about 0%, 2%, 4% up to 18% of ferrite in that case. So, so ferrite number, this is represented by this line, and you are having this point here. So, what you see that you have this side is the ferrite percentage, this is the ferrite percentage. So, we are talking about this 10.7. So, we are getting this 10.7. So, this 10.7 is the maximum ferrite which is available. So, this is for the base metal and this is for the filler wire. So, from this question what you see that you have minimum of the ferrite content what you get is 0% and maximum of the ferrite which you are getting. So, that is basically maximum of the ferrite phase is 10.7%. So, that is clear by the use of this Delong diagram. So, this is how you are going to use so we have already seen the use of the Schaeffler diagram, and then this is how the Delong diagram where the nitrogen is there. So, in that case we can use this Delong diagram. So, next we may have another question like calculate the fraction of pro-eutectoid ferrite, eutectoid ferrite and total ferrite in a 0.2% carbon steel. So, if you talk about the 0.2% carbon steel, you go to this iron carbon diagram, and for the 0.2% carbon steel, if you are coming to again this point or so. Now, at this point, if you have to find the pro-eutectoid ferrite formation. So, pro-eutectoid ferrite will be you will have means before this reaction. So, before this eutectoid reaction, you have to find the pro-eutectoid ferrite fraction. So, this line is for the eutectoid reaction. So, pro-eutectoid ferrite, that is ferrite which is formed before the eutectoid reaction. So, this will be corresponding to this line divided by the whole line. So, it will be 0.8 minus 0.2 divided by 0.8 minus this point. So, roughly if you try to calculate that point, it will be pro-eutectoid ferrite So, it will be 0.8 minus 0.2 because 0.8 is on this line. So, ferrite is line is this. So, you are getting 0.8 minus this 0.2 and then you have to have this 0.8 minus 0.02 something like. So, altogether if you take something like 0.8, so it will be coming close to 75%. So, this way you will get the pro-eutectoid ferrite formation. Similarly, so you can calculate the eutectoid ferrite, you can calculate the total ferrite. Total ferrite means when after the eutectoid reaction, basically you are getting the ferrite as well as the cementite. So, after the eutectoid reaction, so you have that is ferrite plus cementite coming up. So, altogether you will have the total cementite. So, if you calculate the eutectoid ferrite, it will be coming as about 0.22%. If you calculate the eutectoid ferrite percentage, that will be 0.22. So, if you sum them altogether, it will be 0.75 plus 0.22. So, it will be 0.97. So, 97% will be total ferrite. So, this way you can calculate. So, you will have eutectoid ferrite calculation, you will have pro-eutectoid ferrite calculation, and accordingly you can find the total ferrites, that will be 97%. So, these are the different type of questions you can practice on more and more questions, and you can have more confidence when you deal with more questions for getting by using the different types of phase diagrams, and that will help us later in our course. Thank you very much.